Let me use again the word a priori, rate of convergence for free boundaries. Okay, so let me recall the key result of this morning, which I didn't have the time to prove, but I emphasized that it was essential for this discussion, namely that the difference between the exact and the discrete solution in the max norm is bounded by a constant times h squared times the log of h, which I call eta of h. And I said that this was an essential result for the discussion today, this afternoon, but I wanted to also illustrate that this is not enough. In particular, think of this situation where we have an obstacle psi. The solution goes like this. Let's say it touches the obstacle, it stays on the obstacle, and then it detaches. So this is u. Here we have the free boundary. And imagine that we do a perturbation, so we change the obstacle a little bit, or maybe the forcing a little bit. You can see that in this configuration, this point in the one-dimensional picture is going to change by little. Okay, so this is a sort of stable situation where we can hope that perturbation result for the functions will lead to a perturbation result for the interfaces. I view this as a perturbation result for the functions. You can also contrast this with the following situation. Let me draw the same picture. Now this is again the solution, but let me modify the obstacle in a way that now doesn't change the solution. So this in blue is the same obstacle. It doesn't change the solution. So this is the second obstacle. This is the first obstacle. But now you have several points that can be regarded as free boundary points, or points where the solution and the obstacle touch each other. A slight perturbation here, changing the obstacle a little bit, maybe moving the obstacle a little bit down, will make this point disappear. So this is an unstable situation. An unstable situation from the point of view approximating the free boundary. So that tells us that if we want a result that reads something like the discrete free boundary, whatever that means, is going to be close to the true free boundary, we need to get around this situation. Otherwise it's hopeless. And this, in the literature of free boundaries, comes by the name of non-degeneracy. The concept goes back to Caffarelli, early 80s, and it has been used many times, particularly in the context of obstacle problems. So let me make the following assumption, so-called non-degeneracy assumption. That f plus the Laplacian of psi is strictly negative. Not necessarily everywhere, but certainly close to the free boundary. And let me assume, for simplicity of this discussion, that the psi is 0. So I only have f, even though this is not essential. So this is the key assumption. From the standpoint of the application, the physics, remember here in this part of the boundary, we have that the Laplacian of u is equal to f. If we have a negative f, that means there is a force in pushing down, okay? And so the function has to adhere to the obstacle. This is a stable situation. The sign is strictly negative, so this push down makes the function u change very little. I mean, not so much a function, the interface, very little if we change f. So this is a key assumption that was used by Caffarelli in the following sense. So I will review very quickly some of the results because they have to do with the analysis that I want to explain. So the first result, let me call it proposition 1, all due to Caffarelli, is so-called non-degeneracy measure. And it goes like this. The set, let me call it gamma epsilon, is defined as the set of points in omega such that the function u is bigger than 0 but less than epsilon squared. This set is not big. In fact, satisfies that the measure of the set intersection a compact set is bounded by C that depends on K times epsilon. This is for all compact sets containing omega, and the constant, well, maybe let me say it, and the constant depends on several things, certainly depends on K and other things. And so on. So, pictorially, if we have this situation that the solution is 0, this is the free boundary, the solution has to leave the free boundary with the prescribed growth in measure. So this is a quadratic growth. Of course, in more than one dimension, that doesn't mean that we will have a normal, and if we look in the direction of the normal, there will be a quadratic growth like depicted there. So this is a result in measure. So if we move away, this is u equal to 0. If we move away from this set, this is the set gamma epsilon. This set is like a strip in the sense of measure. Okay. And yeah, certainly I forgot there is a lambda dependence on the C, otherwise this would not be true. So let me write it down. Okay. So that's the first result I wanted to mention. There is a second result, also by Caffarelli. It's, I call it non-degeneracy. That goes like this. Say we have a point. That belongs to the closure of the non-contact set. So it can be on the free boundary, and R is bigger than the distance from X to the boundary. Then there exists a constant C such that the following happens: the sup of u of y minus u of x, y here is on the boundary of the ball, center at x. So I'm looking at the point x. Maybe here is the set, the coincident set, contact set. Here is the non-contact set. This is the point x. We are looking at a ball. There has to be a point on the boundary of a ball where the function u grows strictly quadratic. And this again the C depends on lambda and on the dimension. Let me call it D. So this is not a difficult result, it's a maximum principal result, and but I'm not going to prove it, I'm just going to use it, as you will see in a second. This leads to the following statement, also by Caffarelli, which is about the Hausdorff measure of the interface. So again, we have a compact set. Maybe the boundary is not that bad, let's say it's Lipschitz. This is not essential, but it's important to do some integration by parts. Then there is a constant. Very much like in proposition 1, such that the following happens: the Hausdorff n-1 measure of F intersection K is bounded. So in the sense of measure, in the sense of the Hausdorff measure, the interface now is a n-1 surface. This doesn't mean it's made of regular points, so points where it's smooth, but at least the singular points are not too many or not too bad. And there is another result. I will call it non-degeneracy in distance. That again, let's say we have a compact set, not with this Lipschitz boundary. So now let me give an epsilon positive, and let me define a strip. I call it S epsilon. This is a set of points in omega such that the distance to the free boundary is bounded by epsilon. Then maybe I should not call it like this. It's not quite appropriate, this title. Let me call it non-degeneracy 2. Then this strip intersection K has a measure that is also bounded by epsilon. That has to do with the property that the Hausdorff measure is finite, and you can cover with a finite number of balls with size epsilon. So this is just a simple consequence of this deeper result. And let me conclude this with another result. It's a consequence of regularity theory. Let me call it non-degeneracy in distance. So let F intersection K is this compact that we have, be made of regular points. Regular in the sense of regularity theory. So there are flat points where eventually the interface is going to be C1 alpha. Then gamma epsilon intersection K is contained in the strip around F intersection K. where C depends on lambda. So in other words, if the points are regular, like in this picture, and if you take a strip around with sufficiently big, there is a C here, then it will contain the set gamma epsilon that was only defined up there in the sense of growth of U. So these are the key ingredients from the regularity theory that we need for the convergence of interfaces. So let me show now how that can be achieved. Okay. Okay, so let me now introduce what I call discrete non-degeneracy. So very much in the spirit of this morning, I'd like to know to what extent the discrete solution, I call UH this morning, is going to have properties similar to the continuous counterpart. Okay, there will be things that will be difficult to do or maybe impossible to do, but there are things that are doable, and they are essential for the proof of the convergence of the interfaces. In particular, we have the following result. Lemma, this is a discrete non-degeneracy. By the way, these results go back to Brezzi and Caffarelli. So now we have two constants, gamma naught, H naught, such that the following happens for all H that are not too big and points in the non-contact set, discrete non-contact set, we have the following. Provided R is less than the distance of Q to the boundary. So this result here, as you see, is a discrete version of this result. It mimics the result entirely. So I will not have time to prove it. The proof is in the notes that will be available to you. They will be ready after the lecture. But let me mention that in order to prove this result at the continuous level, you have to construct a barrier function. To show this quadratic behavior, you basically write a function like this and subtract from a quadratic function. A quadratic function like x squared has a Laplacian that is strictly negative. So in order to implement this, the question is, what happens if you take a quadratic, interpolate it, and look at the discrete Laplacian? And that's a way to mimic in the discrete level what happens at the continuous level. But we are talking about a sign of the Laplacian, even though it will be discrete, and then in order to do that, you need, as an ingredient, the discrete maximum principle or the weak acuteness that I mentioned this morning. So I just mentioned briefly what is involved here is the discrete maximum principle plus a barrier construction. Okay. All right, so let me state the theorem that I want to briefly discuss. This is the rate of convergence in measure. Again, we have the compact set that I mentioned before. So we have the following. There are two constants, C and H naught, such that the following happens. We look at the symmetric difference between the non-contact sets, the continuous non-contact set and the discrete non-contact set. This is bounded in measure by C times the square root of eta, provided that H is not too big. Remember, eta is the rate of convergence for the solutions, for the functions. The proof is elementary, so let me illustrate the proof with a picture. So let me draw a picture. Let's see, do I have color? Let's say, do you see this? Let's say this is our function u, and let's say that here we have our function uh. Okay? All right. And now, okay. Now suppose that we take a point on the set where the function u is 0. So let's say that we have u so I take a point here, q, and I have a ball where the function u vanishes. Okay? Now, with the function, if the function uh happens to be positive at this point, then because of this theorem, there will be another point within the ball. So if uh happens to be positive here, there will be another point where the difference between these two will be r squared. So now if r is big enough, because we are within the contact set of u, the error between uh and u, this one here, if r is big enough, will exceed the eta that is given by the theorem this morning. Okay? So the function uh cannot be positive here, it has to be 0. That means that the set of points where the uh is 0 cannot be too far from this point. Okay? And then you have a dual argument for the other part, which uses the non-degeneracy of u instead of the non-degeneracy of uh. Okay? So perhaps it's easier to see these things if you, instead of a quadratic growth, you think of a linear growth, which would be the behavior of the derivative. If this is the behavior of the gradient of u, and we have a similar behavior for the gradient of uh, because they are not degenerate, having a control of this, which is basically what is written in that statement, gives us a control of this, which is the difference between the interfaces. Okay? But everything is phrased in terms of U that has quadratic growth. Okay, so the proof is just an implementation of this idea, which is a simple idea, and it goes by contradiction, assuming that you violate, that you are too far, and then you see that because of the growth, because of the quadratic growth, that cannot happen. Okay. However, all of this is a priori, in the sense that, as I said this morning, it involves quantities that are not quantifiable. Regularity, in particular, the solution and the obstacle. So what I'd like to do next is to explain something that perhaps for this audience is less familiar, is less known. How many people here know about posteriori error analysis? Not so many. Okay. So let me say a couple of words about this. So the second topic, which I'm going to describe quickly using the computer, is about a posteriori error analysis. In L infinity. This is not a standard because I'm using the maximum norm, but as you see, the maximum norm plays a role in approximation of the interface. So what do I mean by this? So I want to go from qualitative, which is the discussion so far, to quantitative. So what do we have in the linear case? So let me say a couple of words about the linear theory, for those that are not familiar. Say, suppose that we have this problem, which is what happens for us in the non-contact set. This is in omega. Say we have zero boundary condition. And let's say that we have a function UH, which is our finite element approximation. Okay? This is something we compute. So it's, for us it's known. F is known. So with this function UH, we can compute, imagine that we have two adjacent elements, let's say T minus and T plus. Let's think of the normal going from T minus to T plus. In T minus, I have, say, UH minus, and in T plus, I have UH plus. So these functions are pieces linear, so the function is continuous, so there is a kink on this side. I'm going to quantify that by computing the jump of the gradient. This is the jump of the gradient, and I'm going to call it J sub H. Okay, so in fact, if you compute the discrete Laplacian of U in the sense of distributions, if you compute the Laplacian of U in the sense of distribution, you will end up with this delta supported on the interfaces. So it's possible to prove the following, that the gradient of U minus UH in L2 is bounded by a constant, an interpolation constant, times the following quantities: H plus the Laplacian of UH F times H in L2 plus, and let me write down this, let me call this S so there are two terms, one that is defined, this Laplacian is defined element by element. So there is something that is called an interior residual, which is by how much the discrete solution misses to be the solution of the equation. This is a defect measure of the satisfaction of this identity. So this is called interior residual, and this is called the jump residual. Notice that this is scaled by H, h is the mesh size, and this is scale. Here I have squares. Okay, so the natural scaling is h to the 1/2. Okay, this comes from approximation theory, theory of finite elements, and basically the result is due to Babushka and collaborators. There is a modification of this result. U satisfies this equation. No, UH is a Galerkin solution. It is a finite element. It's a Galerkin solution. It doesn't have to be finite elements. It can be wavelets. It can be spectra, but it has to be Galerkin, because Galerkin is what gives you the approximation in terms of weighted norms instead of negative norms that you will not be able to evaluate. That allows you to go from negative norms or the residual to weighted norms measured in L2. So it has to be Galerkin for this. Okay, the result that I wanted to mention is that there are variations of this. This is the standard theory, and it has many applications and extensions, but we need to measure this in L infinity. So there is a similar result. Now measured in L infinity. And let me call by this I made the skeleton of the mesh. The union of all inter-element boundaries. Okay. Now we go from, as I said, from qualitative to quantitative in the sense that what is written here on the right hand side is computable. We have f, which is data, we have UH, we can compute the Laplacian. For piecewise linear functions, the Laplacian is 0. This is inside the elements, so we just get f, and we can compute the jumps. So we can evaluate the right hand side, we can even evaluate it locally at elements or patches, and we can decide whether we are happy with the right hand side or it's too big. If it is too big, we can act and do a refinement. So this is quantitative, and it replaces what this morning were norms in terms of U, in terms of F, and so on. So what I like to show is how this theory translates to the obstacle problem and how that can be used to approximate the interfaces. And that will be quick. And now I need Vincenzo to help me with the monitor. He was attentive. Okay. So I'll switch. I have the notes written, but I thought that it would be better to use the computer because I need to show you some simulations, and that I will somehow speed up the process. Can you read this little page? Anyway, here is a review of assumptions. This is again the problem of this morning. I have an obstacle, I'm assuming that to be, say, Helder. Doesn't have to be smooth. Okay, this is the basic setting of this morning. We have again the discrete convex set as defined this morning and the discrete solution. And the question that I like to raise is whether we can approximate the difference between U and UH in L infinity in a computable way, a posteriori. And whether, with the second question, we can use that to get information about the approximation of the free boundaries. Okay. It turns out that this sigma that was this multiplier this morning, okay, again the same quantity that I defined this morning, plays a critical role. Okay? And it's sort of simple to understand if you think like this. We have our domain. Somewhere here we have a contact set. Here u is equal to psi. Here u is bigger than psi. This is the non-contact set. In the non-contact set, the Laplacian of u is equal to f. So it's natural that we measure the approximation of u in terms of f. Remember, f is what appears on the right-hand side of these estimators. But when we are here, we can change the value of f locally within this set. We can make f more negative. It will not change anything. It will not change the set. It will not change the solution. So if we modify f inside this set, this will not alter the solution of the problem. So the question is how we read the information. This is a nonlinear problem. How we read the information about u, about the contact set from the data. The data is f and psi. And this is, in the continuous case, is built into the sigma, because sigma tells us where the contact set is. This is precisely where sigma becomes negative. But we don't have access to sigma. We only have access to discrete data. So it's a natural thing to ask whether we have a discrete counterpart of sigma, which I call sigma h. And the goal would be to construct something that would allow us not only to dominate the error, but also to localize it. That the quantity that will dictate the error, for instance, will not be, that whatever depends on f will not be active inside here, because f does not have any influence on the contact set. So it looks like no obvious how to do that. So this is a way to do it, at least one way to do it. These are contact points, okay, that are defined in the sense that f plus the discrete Laplacian of the discrete obstacle has a sign. And then you can split the domain into two discrete parts, one where you have full contact and the other one where you don't have full contact, the complement. And within these sets you have boundaries, inter-element boundaries that are labeled with the 0 and the plus. So these are collection of boundaries of elements. On the boundaries of elements, we will have defined the jump, very much the same way I did for the continuous problem. Then we define this object, looks very mysterious, is not discrete, really. It has two parts, one definition on the contact set, another definition on the non-contact set, and as you see, it's split in terms of the functions, the basis functions, the hat functions Vz. Okay, these are the parameters that are defined at each node that I defined this morning. Phi here is any generic function in H10. So you have these two parts. In the omega plus, as you see here, the positivity preserving operator that I introduced this morning comes in. But this is a complicated definition. It will not be that much complicated if you use the same definition. But the reason here we don't have the pi is that when you introduce well, I mentioned it on the top. This has the right cancellation properties within the contact set. Okay, here. Otherwise, you would not have the right cancellation properties. However, it's not a computable quantity, but it will not enter in the estimates. The estimates, as you will see in a second, depend on these things. They not depend on the definition of sigma. Sigma is a quantity that is good for theory. It depends on these quantities, okay, f and the gradient of uh against a test function phi z. Phi z is a hat function. This has a sign because it comes from the variational inequality. Okay. In order to connect with the continuous solution, we defined what is called, we call the Galerkin function, an idea that goes back to Fesser, Andreas Fesser, and it's defined in this way. You see, you have u minus uh, you have the gradient of that, and you have here this measure, this multiplier, sigma minus sigma h. This would be the natural thing to do if you have a linear problem. If you replace the gradient of u and sigma by what they satisfied, you get the function f. This comes from the continuous problem. So you see the gh is a functional that is completely computable. It depends on UH, F, and sigma H. Okay, so we have a error representation in terms of GH. As I said, this reduces to the regular residual for linear problems, which is the case when sigma H and sigma are 0. But it's very important to get control of the error for the obstacle problem. So how do we proceed now? Let me explain this couple of words. Here is the estimator. The first two terms are the ones that I wrote for the continuous problem, for the linear theory. You have F, you don't have the Laplacian of UH because it's 0, and you have the jumps, scaled with the powers of H that correspond to linear theory. And these are things that have to do with the nonlinear effects, the presence of the obstacle and the approximation of the boundary data. So with that in mind, which I'm not going to get into the details why is this true, the following happens. You get an estimate for the difference between U and the discrete solution, which I call capital U instead of UH here, and the multipliers by basically the same estimator that you have in the linear theory. Okay, this thing plus this correction. The log is very much what you get in the linear in the a priori theory. So how do you get this? What is the idea of the proof? Okay, so let me explain this couple of words. This morning, in order to do the error analysis in L infinity, I explained that we start from the function u and we construct a projection of u. I call it the risk projection, and from here we constructed super solutions, discrete super solutions. They were this plus a correction, and then sub solutions that have here a minus. So the idea was we start from the continuous function, go to the discrete, and at the discrete level use the discrete maximum principle to compare with UH. This is the completely dual approach. Here we start with UH, and we have to reconstruct the UH. In order to reconstruct the UH, we are going to get something that I'm going to call U upper star and U lower star. They will be super and sub solutions for the continuous equation. So in order to do this reconstruction, because all the information in the UH is contained in the Galerkin functional, what we do is we solve this problem, this auxiliary problem, where the Galerkin functional is what I mentioned earlier. We construct this W. Okay? So I'm going from discrete to continuous. Now, this function is a function that is an auxiliary function that allows me to go from the UH by a simple modification to do these two. Okay? And once we do that, so let me, for instance, give you, just so you get an idea, a specific form for one of these super solutions. Okay, for instance, the U star U upper star is the following, is, let me do the sub star, is UH plus W minus W in L infinity plus a correction. Okay, so that's the definition. So it has the following property. When you compute the Laplacian of this, you get the Laplacian of UH, which is a bad guy, but that is compensated with the Laplacian of G because with the Laplacian of W, because the Laplacian of W, as you see, contains the GH on the right hand side, and the GH on the right hand side itself contains the Laplacian of UH. So there is a compensation, and at the end of the day, you can prove by an argument, a maximum principal argument, that this function U sub star is going to be below the U. With a similar idea, you can construct the U superstar, and you can show that it's above the U, and then you sandwich the U with something that is related to the UH. So this is a very technical argument. The only thing I want to illustrate here is that it's a dual argument with respect to the a priori theory that I mentioned this morning. Dual in the sense that we start first from U and go to the discrete. Here we reconstruct the discrete and go to the continuous. But there is a catch, something to think about. This reconstruction uses the continuous maximum principle. When we do this and compare with U, we are comparing it at the PDE level. Since we are comparing at the PDE level, there is no mesh restriction. Okay, so this theory does not require that the mesh is weakly acute. Still, we get the control, as you see, of the difference between U and UH. Okay, and here are some experiments. For instance, this is a pyramid, and you see the effect of localization. Maybe the following picture is a clear picture. These are earlier results without full localization of the same problem, and these are meshes with full localization. So here, where there is contact between the obstacle, which is in red, and the solution, in the center where there is contact, there is no need for refinement, because there is good resolution already, and you see there is no need for refinement, even though the function psi is only Lipschitz, and there is a force in here, pushing down. Okay, so this full localization. Now, with this idea, now that we replace the difference between U and UH measured in L infinity by an a posteriori quantity, we can approximate the interfaces. And in fact, we can get under the same assumptions of non-degeneracy for the continuous problem, it's possible to prove that if we take a strip of this radius, is the estimator divided by lambda. Lambda is the non-degeneracy parameter, written here, absolute value of lambda, and then you take the square root. If you take a strip around the discrete interface, the continuous interface will be contained in that strip. So this is a very interesting result, posteriori result. So let me illustrate it with a picture. Okay, so let's say that this is our discrete interface, which is defined, as you see, we take the set where UH is bigger than the discrete obstacle plus the estimator, and we take the boundary of that, so this is FH, and now we take a strip around it. This is RH, which is the square root of epsilon h of the estimator divided by lambda. Okay, this strip we are sure that contains the continuous interface. So the continuous interface has to lie here. This is a fully computable result. Okay, if there is an interface, it has to be within these two lines that we can compute. Okay, the proof of this is similar to what I said before a priori. And here you see some results. So this is a situation. There are 4 pictures where we are changing the value of f, the forcing function. Imagine that the obstacle is like a saddle point. So you have two mountains and a valley, like a saddle point, and you are pushing down. The more you push, the more contact you have, you see the interfaces. These are the barrier. These are barrier set. This is the strip that I mentioned before. Okay. So we know that the true interface is within these two lines. So, for instance, in this picture, we have the occurrence of perhaps of a topological change. Okay. Here there is no topological change yet, and here, well, you see the contact set is now one set, one full set. So the point I want to make is that these two lines represent this strip, and the true interface that we do not know lies within these two lines. So we know that after this calculation that the contact set, the true contact set is here, or that the true contact set is here. Okay? And the same happens in more dimensions. This is a situation in 3D. It's much more difficult to do, so here you have only the outer barrier set. And again, here we are changing the function f from 0 to -7 to -15. Okay. And so how am I doing with time? I'm okay. So I have like 10 more minutes? Yeah. Okay. So so let me summarize the results so far. So this morning I described an a priori theory, starting with H1, and I mentioned the importance of dealing with L infinity. And a consequence of that was the approximation of the interfaces following Caffarelli's work. All that is not quantitative, it's qualitative. Now, if we want to be quantitative, we need to do an a posteriori analysis that relies on discrete quantities or data. And the question is, if we know how to do this for the linear theory, whether that translates into the obstacle problem. And there are two parts of that. I show you that there is a way by duality, by sort of a dualization, to repeat the construction of the super and sub solutions, now at the continuous level. And with that, we get approximation of the solutions. And the non-degeneracy of the continuous problem, plus Y's definition of interface. Notice that I'm not saying this is bigger than psi. I'm adding a correction here, which is computable. This definition avoids the need for a non-degeneracy of the UH, because the non-degeneracy of UH is based on the discrete maximum principle, and I'm saying that the discrete maximum principle is not necessary for this a posteriori theory. So in order to avoid the non-degeneracy, we need to modify slightly the definition of the interface by changing what would be the natural definition by adding something here, which is this estimator. And with that, we get these sets, barrier sets, and the approximation of interfaces. So we get a complete theory that mimics the a priori theory, but is practical, is computable. So I'd like to conclude with an application where variational inequalities enter, that is rather recent. It has to do with electrowetting. You may wonder, why has this anything to do with variational inequalities? And it's a way to represent contact line pinning. So the problem is the following. You have a drop of a fluid, like glycerin, for instance, between two plates. The plates are close together. Maybe here you have dimensions. So the height may be of the order of microns, but the device is of the order of millimeter. So the drop can be modeled by, instead of Navier-Stokes, using a simplification. It's a Helle-Shaw model. The point is that there are electrodes, as you see, and by changing the potential, you create an electric field between the two electrodes, and the drop, which fits the electric field, because it's a charge drop, wants to move from an area of small potential to an area of larger potential. And that motion that is induced by the differential, by the electric field, is quite important to move drops at the microscale. So this phenomena was well known before. But it's very important now in applications, as you see here a number of them. And it has to do with the fact that the microscale, or even nanoscale, surface dominate bulk effects. So with very small voltages and very small electric fields, we can move drops. The question is how to model this. And the model and the simulation is based on this simplification of Navier-Stokes that had to do with what I call a Helleshow model. It has one difference with the usual Helleshow model. It has this term UT because we wanted to account for inertia. The electric field and the voltage will change much more quickly than the fluid will move. And we wanted to account for that here. And then this is the usual thing. If you forget about that, you have U is minus the gradient of P, like the hydrostatic situation. And the boundary condition is what is important. So on the boundary of the drop, which I'm going to view from the top, maybe in this view you will see it better. This is the view from the top with the different potentials. And this is the drop, view from the top. So it's a two-dimensional situation, a Helleshow model, and the interface has a boundary. On that boundary, the condition is that the pressure is the curvature, that has to do with the Young effect. And there are two terms, one that has to do with pinning, contact line pinning, which is the one that I mentioned before, that can be modeled via variational inequality, because it has a sign function here. What this term tells you is that the drop, imagine that you have a drop on a substrate like a table, and you incline the table a little bit. The drop will deform a little, but it will not move, because there is some sort of friction with the substrate which is not completely flat. That sort of friction we are modeling with this term. So you need some force beyond a certain threshold for the drop to move. This is a very simple model that related to friction. And that's where the variational inequality comes in. Well, here you have some references of work in this direction, and in particular this has been developed with my former student John Walker in a couple of papers. So let me show you what happens. So again, here you have a situation where you have several electrodes with different voltages, as you will see in a second. Let me run this. And you see the drop moving according to the voltages. When the voltage is larger, it moves in the direction of a larger voltage. The solid line is the experiment, and the dotted line is the numerical computation. So you see a reasonable agreement not only in space but also in time. And there is only one parameter here, is this fitting parameter. Okay, this parameter is determined by experiment. So this is a one parameter problem. So for one parameter problem, I think that the result is pretty reasonable. So the agreement is not perfect, but it's good for design. Here you have a situation where you have voltages very large on the two electrodes on the sides and small in the middle. And as you see, that pushes the drop apart, and eventually there is a topological change. So I will say more about this type of flows next lecture tomorrow. Again, you see, let me run it again. You see good agreement in terms of the dynamics, even the splitting time. But at the end of the day, the drops are not circular. Okay, they are not circular because this is a situation where the drop gets stuck. Okay, a circular drop would be a drop in equilibrium in a medium that doesn't have any friction. And to conclude, let me show you a couple of meshes. So here is the experiment where the meshes are deforming, the previous experiment where the meshes are deforming, and there is a topological change. And depending on how you define the topological change, you may have satellite drops, as you see here forming in the middle. So let me see if I have, here you have a zoom of the region in the middle where there is this topological change. So this is the drop that forms first, and because of inertia, that's why I wanted to include it, there is a second topological change. So I will mention tomorrow, but the purpose of this simulation is twofold. First, to show you that variational inequalities appear in various ways, even in problems that are very recent, had to do with electrowetting in particular. and the techniques that I explained apply, but there is no full theory for what I discussed. There is a lot of open problems, in particular the continuous equation. We do not know whether there is a solution, not even for short time. There is, as you see, topological change. We don't know if there is a reasonable concept of solution beyond topological change. And because of that, the numerical analysis of the problem is very precarious. We cannot do an error analysis of something we don't know even that exists. So there is partial analysis for this problem, only partial analysis. And the second reason I brought it up is because here you have, in a sense, a gradient flow, and I want to talk about gradient flows tomorrow. There will be several aspects of that, and techniques to handle topological changes, as I mentioned here, are very important. The technique that is used is a parametric technique, but it has to be combined with a technique that allows for topological change. There will be more of that in the third lecture and the fourth lecture. So I'm done. Thank you.
Any question? Comment?
Just a question, suggestion. When you, for this a posteriori estimates, rather than keeping the singular terms with the jumps, I would say that the natural point of view would be to smooth out the UH by a convolution, and then you have a nice function, then you can compute everything. I mean, everything becomes function, and you get more standard estimates. Of course, with an error of convolution, but that you know how to handle the error.
But why would you do that?
Just to avoid the singular term, which is not
You mean the jumps?
which is a Dirac mass on the interface.
No, but the jump is easy to compute. The jump, you have piecewise linear functions, and then you have linears on each element. The gradient is a constant. You restrict it to a side, which is a line or a simplex. So this is easy to compute.
Yes, but it might be that the convolution is closer to the exact solution.
Well,
Itself.
this is possible. In fact, when you average, you typically get better results. But you have to be able to average in a smart way. For instance, if you average with a kernel that has a radius of age, so if you only see few elements, then you don't get much. If you have a kernel that has a larger averaging, like square root of h, maybe you get something more. Okay, so it's not completely clear. But again, in this context, remember there is no age. H is a local object. So if you move away from a triangle, the next one can be quite different. The transition between small and large is rapid. So convolution is something you need to do very carefully. So if you had, you could do it, but you would need an epsilon that is space dependent. The epsilon maybe has to zoom more or less depending on where you are in the domain. So it becomes a little tricky. You could do things like this, but I mean for our purposes, which is to estimate the error, this is okay. If you want to say do what you could call a post-processing of the solution, given the UH, you want to do something that improves the UH and gets a better result, then you are correct. But we are not trying to do that. We are trying to estimate the error between the true solution we don't know and what we computed. And the quantities that we have at hand are rather reasonable. A second part of the answer to that is that there are estimators that are more sophisticated than the ones that I mentioned. These are the simpler ones. And for people that are not in the field, these are already a bit complicated. But you can do some averaging. And the engineers tend to do that, precisely because of the reasons you mentioned. It's like a convolution, but not quite in the sense of you put a kernel. It's called Sienkiewicz-Zoo estimator. You do some sort of mean within stars, or patches of elements. And that defines something that has better approximation properties. Better, it means generically they have better approximation properties. But you can construct counterexample where there is no gain. But generically, for problems that are of engineering interest, they see better results in terms of approximation. So there is something true in what you are saying. So I chose the simplest estimator possible.
Thank you.
But there is another question, but maybe we leave it for later.
Okay, if you have more questions, maybe ask a professor or checker during this day and tomorrow.
There are notes about what I talked about. I didn't.
Website, PDF file.
We have to
We
discuss
put it-
maybe.
yeah, we discussed that.
The notes
Yeah,
will be
then-
handed around.
Yeah, or hanging around, or maybe put some
Probably in
website,
PDF.
PDF file. Okay, let's thank Professor.